When we finished up last time, I was talking about simply applying the paraxial ray trace equation from surface to surface as the light propagates through the optical system. Ray hits a surface. Let's say it starts from the object, it hits the surface. It will refract and change direction. It will then continue on. When it hits the next surface, it refracts and changes direction and continues on. But when we're doing paraxial ray tracing, we actually get to break that process down into two distinct steps. When the ray hits an index boundary in the infinitesimally narrow region right at the index boundary, the ray will refract. If it's a reflecting system, of course, it will reflect, but rather than say refract or reflect, I'm just going to stick to refract for our purposes here. So at that region, just at the index boundary, the ray refracts. It changes directions, but the height stays the same. The height doesn't change until it propagates some distance at this new direction. So after the ray reaches a surface where it interacts and refracts, then the ray will propagate, and the property of the change in direction is this calculation we just looked at a few moments ago. When the ray then the ray is going to propagate through some material of a constant index of refraction. At this point, the direction that the ray is propagating at, its slope, if you will, stays constant, but the height changes. And the height changes, the new height being a function of the initial height and the new slope angle and the distance, propagation distance that the ray has traveled. Okay. We can also bring this down to what's referred to as a reduced thickness, where we simply scale by the index of refraction. And again, we simply apply these processes sequentially as the light propagates through the system. Ray travels from the object to the first optical surface. We're going to apply this equation. The ray hits the surface. We apply this equation. The ray propagates in the new media. We apply this equation. It hits the next interface. We apply this equation. So we just keep applying these simple linear equations as our light propagates through our optical system. Now let's go back to a thin lens in air, and I'm going to just do a simple calculation, and I'm going to talk through this. Obviously, I'm not going to ask you to solve it right now, but if I had a thin lens in air, index of refraction of air is 1. The lens has a focal length of 100 millimeter, and I've got an object that's 250 millimeters to the left of the lens. So I want to know, where is my image formed? Well, I'm going to assume, since I didn't say anything, well, I did say it was a thin lens in air, so object space media and index space media are both index of refraction 1, air. Z, my object distance, is minus 250. Remember my sign convention. Because it is to the left of my lens, it's going to be a negative distance. And what I want to do is find Z prime, where my image is located. So I can use my equation from from the previous lecture, and the one before that. So 1 over Z prime, again this is index, is equal to 1 over Z plus phi, and if my focal length is 100, my power is 1 over 100, and if I do the math, the 1 over Z prime is equal to 0.006, so Z prime is about 167. So my image is formed 167 millimeters to the right of the lens, which means it's 417 millimeters from the actual object position. Another way of doing ray tracing, and I'm not going to concentrate on this one as much during the class, although it is extremely useful, is to do the ray tracing in terms of matrices. Okay. Any ray paraxially is defined in terms of two properties, its height and its slope. So we can define any of our paraxial rays simply by using a two-element vector. So our vector is simply a function of height and slope. Y being the height at a surface, and u being the ray propagation angle or the ray slope in that optical space. We can set up a series of ray trace equations, again, an equation for refraction and an equation for translation. And the nice thing about the matrices for refraction and translation is they are both unit matrices. So in optical space, y prime and omega prime is a function of this matrix acting on the original height and optical angle. For translation, again, I can calculate the new y prime and omega prime by applying this matrix to, again, the original ray conditions. And you'll notice in this case, when I have refraction, y prime is equal to y. Y doesn't change with refraction. When I look at the translation, omega prime is equal to omega. So only the height changes or only the angle changes. So if I have a complicated optical system or even a simple optical system, all I need to do is to create a system of matrices that allow me to transform the path of the ray as it propagates through my optical system. Okay. We're going to perform those operations from right to left, which is typically the opposite of how we think of our light being propagating through our optical system, but effectively over here is object space, and over here, if you will, is our image. So the first thing we do is to propagate some distance in our initial media. Then we refract at the first surface, and this is for a simple case of I'm going to assume this is a single lens. So we refract at the first surface, propagate through that lens that has some index n prime, refract at the output face, and then travel in image space media some distance until we reach our image location. Now, if we were to take the basic system matrix, now in this particular case it's only for a single lens, but of course we could apply this for as complicated a system as we would like, we can create what's called an ABCD matrix for the optical system itself. So we've got our object space propagation, image space propagation, and then our ABCD system matrix. Now we can also calculate the matrix for the whole system, the matrix that takes us from the object to the image. And if we do that calculation, it looks something like this. And it might start to be looking a little bit ugly, but remember, each of our individual matrix elements were unit matrices, which means the system matrix must also be a unit matrix. So our properties at our image are a function of this object to image matrix acting upon our initial ray properties in terms of height and slope. Okay? We can also use this matrix ray tracing calculation to determine a lot of the paraxial properties like those we've already talked about. How about the magnification? Magnification is simply the ratio of the object height to the image height, and we can calculate our image height using our system matrix, and you'll notice we have a term that's dependent upon the initial height and a term that's dependent upon the initial angle. But paraxially, magnification is independent of angle, so this term of that matrix must be equal to 0, which tells us that since my magnification is image height to object height, my magnification is simply this term right here. Okay. Now remember, we've now set this term to be equal to 0 in our M00 prime matrix. We have a unit matrix, so what we can also do is determine that the value of this coefficient, this term in the matrix, simply because the product of 1 and 1 over m is equal to 1, we have a unit matrix, so this term in that previous matrix must be equal to 1 over the magnification. So let's calculate the system power. Let's assume we have an object at infinity. We're at infinite conjugates. By definition, the slope angle, the slope of the rays coming in is 0. They're coming in parallel to the axis. Well, our omega prime is equal to this term in the matrix. Okay, but again, this was 0. Omega is n times u, so this is 0, which says our final angle is cy. C is the final slope divided by the height. That's our power, so the inverse of the focal length. We can also calculate the separations between the vertices and the principal points. Part of the reason for talking about the matrix form of ray tracing is not that you're going to want to do this when I want you to do some first order calculations, although I do find them to be quite useful. The key with these is this is how most ray tracing programs actually do ray tracing. They use some form of matrix approach for doing the calculations, and that's why I wanted to introduce you to this technique today. So thank you very much for your time, and we will continue again shortly.